Thrashing workloads. We analyze LIP and BIP in detail using three memory intensive benchmarks: MCF, ART, and Health. These benchmarks incur the highest MPKI for the spec int spec FP and Olden benchmark suits respectively. The LRU policy results in thrashing as the working set of these benchmarks is greater than the baseline 1 MB cache. For all experiments in this section, a value of epsilon equals to 1 by 32 is used. The MCF benchmark, figure 2, shows the code structure from the implicit.c file of the MCF benchmark with the three load instructions that are responsible for 84% of the total L2 misses for the baseline cache. The kernel of the MCF can be approximated as a linked list traversals of a data structure whose size is approximately 3.5 MB. Figure 3 shows the MPKI for MCF when the cache size is varied under the LRU policy. The MPKI reduces only marginally till 3.5 MB and then the first knee of the MPKI curve occurs. LRU results in thrashing for the baseline 1 MB cache and almost all the inserted line are evicted before they can be reused. Both LIP and BIP retain around 1 MB out of 3.5 MB working set, resulting in hits or at least that fraction of the working set. For the baseline 1 MB cache, LRU incurs an MPKI of 136. Both LIP and BIP incur an MPKI of 115, 17% reduction over LRU, and OPT incurs an MPKI of 101, 26% reduction over LRU. Thus, both LIP and BIP bridge two-thirds of the gap between LRU and OPT without extra storage. We can see in the graph of MCF and that on the x-axis it is cache size in MB, and on the y-axis it is misses per thousand instructions. So when the cache size is less, we can see the misses are more, and when the cache size is more, we can see the misses are less. uh, these are mpki versus cache size for mcf and arc. Well, this diagram uh, shows what. Well, this is figure 2, miscausing instructions from the mcf benchmark. This is while this is something like as arc in tall equals to arc in tail. Cost is 84% of all L2 misses, 28% by each instruction. If tail to time plus asin to org cost is greater than, if tail time plus asin to org cost is greater than latest, arsin equals to arc t uh, into and the tail mark continue arsin. I don't get this code. Anyways, let's move forward to the art benchmark. Figure 4 shows the code snippet from the scanner.c file of the art benchmark containing the two load instructions that are responsible for 80% of all the misses for the baseline cache. The first load instruction traverses an array of type F1 layer The class of F1 layer defines it as a neuron containing 7 elements of type double and 1 element of type pointer to double. Thus, the size of each object of type F1 layer is 64 byte. For ref1 input set, num f1s equals 10,000. Therefore, the total size of the array of f1 layer is 64 byte into 10k equals to 640 kb. The second load instruction traverses a two-dimensional array of type double. The total size of this array is equal to 8 byte cross 11 cross 10k equals to 880 kb. Thus, the size of the working set of the kernel of Arth is approximately 1.5 MB. Figure 3 shows the MPKI of Arth for varying cache size under LRU replacement. LRU is oblivious to the knee around 1.5 MB and causes thrashing for the baseline 1 MB cache. Both lip and bip prevent thrashing by retaining a significant fraction of working set in the cache. For the baseline 1 MB cache, LRU incurs an MPKI of 38.7, LIP incurs an MPKI of 23.6, 39% reduction over LRU. Uh, BIP incurs an MPKI of 18, 15, 4% reduction over LRU. And Opt incurs an MPKI of 12.8, which is 67% reduction over LRU. Both LIP and BIP are closer to OPT. The access to array bus TITJ brings in cache lines that are not used in later iterations. Lip retains these lines in cache while BIP can evict these lines. Hence, significantly better MPKI with BIP compared to LIP. We can see the code over here. Num1s equals width into height. Num2s equals num objects plus 1, which is like 100 into 100 for ref input set and plus 1 for ref input set. For tj equals spot, tj is less than num2 tj plus plus y tj dot y equals 0. If y if not equals to y tj dot reset. For ti equals to 0, ti less than num funds, ti plus plus. This is causes 41% of all L2 misses, causes 39% of L2 misses, f1 layers ti dot p into p. This is a code that I don't understand again. The health benchmark. Figure 5 shows a code snippet from the health.c file. It contains the pointer dereferencing load instruction that is responsible for more than 70% of the misses for the baseline cache. While list is not equals to null, p list patient, list equals to list forward, causes 70% of all L2 misses. Miss causing instruction from the health benchmark. Okay. The health benchmark can be approximated as a microkernel that performs linked list traversals with frequent insertions and deletions. The size of the linked list data structure increases dynamically with program execution. Thus, the memory reference stream can be approximated as a cyclic reference sequence for which the period increases with time. To show the dynamic change in the size of the working set, we split the benchmark execution into 4 parts of approximately 50 million instructions each. Figure 6 shows the MPKI of each of the 4 phases of the execution of health as the cache size is varied under the LRU policy. You can see over here, this is the plot for 0 to 50 million, 50 million to 100 million, 100 million to 150 million, and uh, 150 million to 198 million. During the first phase, the size of working set is less than the baseline 1 MB cache, so LRU works well. However, in the other three phases, the size of the working set is greater than 1 MB, which causes thrashing with LRU. For the full execution of health, LRU incurs an MPKI of 61.7, LIP incurs an MPKI of 38.5% reduction over LRU. BIP incurs an MPKI of 39.5, 36% reduction over LRU, and OPT incurs an MPKI of 34, 45% reduction over LRU.